Okay, we're continuing with Chapter 8 in the Trigonometry textbook. Right now, we're learning about complex numbers. The majority of this chapter, 4 out of the 6 sections, are on complex numbers. And this is really interesting because in the algebra playlist, the algebra textbook, there was just one section on complex numbers, but here in trigonometry, we're going a lot deeper. And so, in this video, we want to understand the trigonometric or polar form of complex numbers. So what they're talking about here is that, as I mentioned in the first section, we can think about all numbers as existing in the complex plane, all numbers that exist in mathematics, right? You draw like this. See here the complex plane. Here's the imaginary axis. Here's the real axis. So and actually I believe in section 1 I put this R here. I don't think you're supposed to do that when it comes to the complex plane, or like put like this I for the set of imaginary numbers, the set of real numbers. You're not supposed to do that. I don't believe. You just put like this. This is the set of all complex numbers, and then you just put like RE and IM here. And then I think the convention is you don't. Here, the imaginary axis is not like I, 2I, 3I. You just put another real number axis. So you just do 1, 2, 3. -1, -2, -3. But when you go along the imaginary axis, it's implied that that's associated with an I. So all numbers that exist in mathematics are represented as being in a plane like this. It extends infinitely in all directions, right? That's a plane. So again, all numbers that exist in mathematics are represented as being in a plane like this. So you could have a number be out here, right here. This is a number that's represented as 2 plus 3i. Okay, and so all we're doing in this section is you can see that I just located this complex number from a rectangular standpoint. So I went x and then y, plus 2, then plus 3. So this is like represented from the perspective of a rectangular coordinate system. Okay, but all we're doing in this section is we want to represent all complex numbers from a different coordinate system perspective, from the perspective of a polar coordinate system. And in the process, to do that, in the process, we're going to have to use trig functions. And so that's it. That's the idea of this section. So, okay. It says the complex plane and vector representation. So we haven't, the textbook hasn't officially introduced the complex plane yet. I've introduced it, but this is, as far as the textbook goes, this is the first time they're going to talk about it. So unlike real numbers, complex numbers cannot be ordered. One way to organize and illustrate them is by using a graph and a rectangular coordinate system. Yeah, so we can order real numbers on a number line like this, right? But we can't do that with complex numbers, at least on a line, because complex numbers are two-dimensional. In the sense that, so when you think about the idea of dimensional, it's like, so space is three-dimensional. And all that's saying is that to describe all the location of all points in space, you're going to have three separate distinct parameters. There's no other way to do it. You can pick any kind of coordinate system you want, rectangular, spherical, cylindrical, whatever. No matter what you do, if you're going to try and represent all points in 3D space, you're going to have to use 3 separate parameters. But like, if, for example, though, like time or weight or temperature isn't like that. You just need one parameter to describe like the time of something. So like from my perspective, it's one dimensional. It's weird that it works that way, but that's just how it is. Okay. And the way you can think about it from a like a mathematical standpoint of the meaning of one-dimensional, two-dimensional, etc., is that so if I have 3 minus 2, okay, well, we know that we can combine these and get one number, one parameter here. And we could do this with any real numbers, okay? But if I have something like 5 plus 7i, I can't simplify this anymore because this is like its own distinct direction you can think about, the I part. And so that's why it's you can think of it like being two-dimensional. And so what they're saying is that we could organize all real numbers on a line, but when it comes to complex numbers, we can still organize them, but it's instead of a line, it's going to be a plane. That's all they're saying. Okay, and again, I think the convention is you can put this like C here for complex plane, but you don't want to do this. You want to do, for some reason, they don't want you doing that. You do, this is the real part, this is the imaginary part. And then you just put these, you don't put i's here. I think the reason why is because if you remember the definition of a complex number, a plus bi, a is the real part, b is the imaginary part. B is the imaginary part, not bi. They call b the imaginary part. So, but what we can do though is instead of doing a plus bi, we can do x plus yi. Same thing, right? But now we're just being more reflective of that. We've got this plane here, and at the center of the plane is the origin of a rectangular coordinate system. Okay, and we call this, this is a complex number. This is called the rectangular form of a complex number. And well, you can say any complex number you can say is z. And this is the rectangular form of a complex number. And it makes sense because you want to think about that. So this is, all complex numbers are in a plane like this, right? All complex numbers are in a plane like this. And so it extends infinitely in all directions. But this coordinate system here is not inherently related to all these complex numbers in this plane. You could take this coordinate system out of here and all the complex numbers are still there in the complex plane, right? We can put any coordinate system we want here. Again, the coordinate system is not married to the complex numbers at all. The plane, the infinite plane of numbers, that's the complex plane. What coordinate system you put in order to aid in locating points in this plane, which represent complex numbers, is up to you. Okay, and so the idea is what we're going to do in this section is we're going to just switch the coordinate system with a polar coordinate system and see, okay, well, how can we locate points in this plane using a polar coordinate system? What's that form going to look like? That's the idea. Okay, but now what it mentions here is that what we can also do, what we have the ability to do, since we're dealing with a plane here, is that once we've gone past like one dimension and into 2 dimensions, 3 dimensions, well, here we're just going to be in 2 dimensions. All numbers that exist in math are just in 2 dimensions. So, but what we can also do is we can bring vectors into this. So, for example, we can say that this complex number right here, one way of looking at it is it's got these rectangular coordinates, but it's also it's represented by a vector that's tail is at the origin and its head is at the point xy. Right? That makes sense. And so why do we want to do this? Well, no, just because if we're trying to understand how complex numbers work, we're going to use all the mathematical tools available to us. If we're dealing with something in a plane, well, then we can bring vectors in. Why not do that? Maybe looking at complex numbers from the perspective of vectors would be useful in some sense. So, but this vector has components, and this vector here would have components -3 and +2. Okay, so let's see. to graph a complex number, such as 2 minus 3i, we modify the coordinate system by calling the horizontal axis the real axis and the vertical axis the imaginary axis. Yeah, so you just want to imagine that it's like, think of it this way. It's like there's this complex plane that's in nature you can think about. There's no coordinate system in it inherently. It's just this infinitely wide, that's what a plane is. Plane of numbers. That's it. That's the complex plane. But how we choose to locate points in the plane is up to us. We can look at it from the perspective of vectors. We can put any coordinate system at the center of the plane that we want. But the plane is two-dimensional. Planes are two-dimensional in the sense that there's two distinct directions that are represented by two distinct parameters. That's the thing. And one direction is the imaginary direction, and the other direction is the real direction. That's the idea. Okay? So they have the imaginary axis, the horizontal axis is the real axis. So vertical axis, the imaginary axis, horizontal axis, the real axis. Then, okay, complex numbers can be graphed in the complex plane. Okay. And then each complex number, it determines a unique position vector with initial point 0, 0 and terminal point A, B. So yeah, a position vector is a vector that has its tail at the origin and it maps out a point. It gives the position of a point in a plane relative to the origin. That's a position vector. So, okay. Let's see. This geometric representation is the reason that A plus BI is called the rectangular form of a complex number. The rectangular form is also known as the standard form. So yeah, the standard form is you can use any coordinate system you want, but the standard convention is to use a rectangular coordinate system, and then here's a complex number in rectangular form where you're going it's these perpendicular axes, and the first coordinate is the horizontal coordinate, and the second coordinate is the vertical coordinate imaginary component. First horizontal component is the real, vertical is the imaginary. And that's the standard convention. Okay. Now, so the next thing they talk about is that we can, if we want to look at this from the perspective of vectors, well, we can think about like vector addition. So if we're adding two complex numbers, you can think about that from the perspective of adding two vectors. Now we know we can do like the parallelogram method, graphical representation of adding vectors, or the tip to tail, and they do the parallelogram viewpoint here, I guess because since we're doing position vectors which have their tails fixed at the origin, they want to do it with the parallelogram method. But yeah, the idea is you start with one complex number or two complex numbers, and you add them, and then that's a new complex number, which is a new vector pointing to that new complex number. And we know from adding complex numbers that all you're doing is just adding the components, adding the x components or the real, and also adding the y components. That's what vector addition is. That's how you add vectors. Okay, and there's the resultant vector. And so here in this example, they do another example of vector addition. But you're adding two complex numbers, right, that are represented by vectors, and you get this resultant vector. So you've got, let's see, adding the vectors, the complex number is 6 minus 2i plus minus 4 minus 3i. You've got 6 minus 4 is 2, minus 2 minus 3 is 5i, and there you go. There's the new resultant vector at 2 minus 5i. Okay. So now, but the main point of this section is that we want to remove this Cartesian coordinate system and then put a polar coordinate system at the origin, at that same origin, and think about, okay, what would a complex number be as far as in regards to polar coordinates? But the way we're going to look at this is that, so we've got this complex number here, right? I just put x and y, but x and y are variables. They could be negative or positive. Like in this case, x would be negative, y would be positive. But we have a complex number here, z. Okay? So the idea is, what would this exact same complex number be, but in polar coordinates, right? I want to communicate to somebody, here's this complex number. With this is the real part, this is the imaginary part. It's really again, it's more about this location in space, this location in the plane is the complex number. Not the coordinate system is not married to the complex number. It's this location in space represents a complex number. How I choose to specify that location is up to me. So if I wanted to specify this exact same complex number, this exact same location in space, which is represented by this here in rectangular form, x plus yi, how could I locate this exact same complex number? Again, I want to make it clear that we're talking about the exact same complex number. How could I locate this exact same complex number, but we're still talking in general though, x and y, with polar coordinates? Okay, so remember, polar coordinates are like it is kind of convention to still kind of leave the XY coordinate system in the background, kind of faded. But technically, we could just remove, let me do that. Technically, we could think about just removing it, and you would have something like, so this is the same origin, like the center of the plane, and then you've got, and then let me put this kind of fuzzy in the background. You can still put a vector to represent we've got, here's this point. Let's say it's the same point right around, I guess, here. Okay, so I'll put a vector to that point. Okay, so the two parameters with a polar coordinate system is this is r. That's the first parameter. And then this is theta, the second parameter. So like this is like r is equal to 1. R is equal to 2, 3, 4. And then theta is just like 0 to 360. It's just like a normal angle, or 0 to 2 pi. And so you can see with these two parameters, you can locate any point in the entirety of the plane. Okay, and here's the complex number z. And theta is measured from like this positive horizontal direction. But typically you'll see polar coordinate systems with the XY coordinate systems kind of overlaid, but the Cartesian coordinate system. But technically there is no Cartesian coordinate system. It's the polar coordinate system, right? So okay, how can we want to represent this complex number in polar coordinates? How can we do that? Okay, well we can start with this here. Okay, let's say we can try and relate these two, right? This is the standard form. We understand how this works. Let's try and relate these two. So, okay, I want to make this kind of faded. So this would be x, y, right? If like in the background is the Cartesian coordinate system. So we can see that, well, from the Pythagorean theorem, r is going to be the principal root, square root of x squared plus y squared. Okay. What else? Well, we can see that x is going to be r cosine theta, and y is going to be r sine theta. And what's nice about the way that trig functions are defined is that it's not like we have to look at this like, we don't have to just use the reference angle theta prime. We can just use the actual theta. And what the usefulness of that is, if we use just the reference angle, it would always, the x and y would be positive every time. But with this theta, it would honor the fact that x is going in the negative direction, and in this case, y is going in the positive direction. So this is perfect. This theta can take any angle from 0 to 360, or even more than that, the coterminal angles as well. But it can take any angle, and it'll honor the sign of x and y. Okay, great. What else? Well, okay, we know that we can say this. We can say something like, so tangent, I guess, of theta prime is y over x, or maybe we want to kind of keep this limited to just x, y, r, and theta. So we could say tangent theta is y over x, talking about this theta. And that's useful. I guess what would happen is we would get this would be a positive or negative ratio. And so we could narrow it down to, if we got a negative ratio here, we know we're in quadrant 2 or 4. Positive ratio, we know we're in quadrant 1 or 3 with the theta, but we don't know which. But then if we got some information about the rectangular coordinates, we can from there figure out what quadrant we're in, and then kind of put 2 and 2 together to figure out what the actual angle theta is. Because if we use this to get theta, we're going to do inverse tangent, and it's going to give us something between minus pi over 2 and pi over 2. So we're going to have to kind of do a little analysis to see exactly what angle we're actually dealing with, but still that we can use this because we know it's going to give us, if tangent theta is positive, we're going to be in quadrant 1 or 3. If it's negative, we'll be in quadrant 2 or 4. And then, but yeah, we'll have y and x, so we'll actually be able to figure out what quadrant we're in. Because like if all we see is just a negative number like 0.707, tangent theta is equal to 0.707, well then all we know is we're in quadrant 2 or 4. But if we know information about, like the specific information about y or x, then we know where the negative is coming from. Is it coming from the y component or the x component? Then we'll know what quadrant we're actually in. So, okay, yeah, there we go. So there's the relation between the Cartesian coordinate system and the polar coordinate system. And with this, we can go back and forth, either direction, going from polar to rectangular, rectangular to polar. Okay, so let me erase these because we can see that that's what they list right here. There's the relationships between x, y, r, and theta, the two coordinate systems. Okay, so now, but what was the goal here? We want, what is z equal to? That was the whole purpose of this. So with our understanding of the relation between rectangular and polar and rectangular, what is z in polar? Well, just substitute what for x was what? R cosine theta, and y was r sine theta. So r cosine theta plus r sine theta. And then let me put a parentheses here so we don't confuse the I being in the argument of sine. So there we go. Now what we can do is, just to make this a little bit clearer, we can factor out the r and get cosine theta plus r times cosine theta plus I sine theta. And that's it. There you go. There's the polar form of a complex number. Here's polar, and here is rectangular. That's it. Okay, so we come here. Now they just officially state the polar form of a complex number. If you've got a complex number in rectangular form, x plus yi, the corresponding polar form for that exact same complex number, they mean the exact same thing, is this, r times cosine theta plus I sine theta, where we know the relationships between r, theta, x, and y. Okay, now this expression cosine theta plus I sine theta is sometimes abbreviated as cis theta, if you want. So in that sense, this would be r cis theta. And you can think about that as like it's r cosine I sine is the idea. Cosine I sine theta. Okay. Now, the number r is the absolute value or modulus of x plus yi. And theta is the argument of x plus yi. So, yeah, here's some notation for you to remember. So notice that they're saying that r is the absolute value or modulus, not of the polar form, but of the rectangular form. So of the rectangular form of so we've got this complex number, z is equal to x plus yi. R of this form R is, you call that the absolute value or the modulus, and theta you call the argument. So if you're looking at a complex number in rectangular form, you can think about what is the modulus of this complex number, or what is the argument. What they're talking about is R and theta, okay? In this section, we choose the value of theta in the interval 0 to 360, but any angle coterminal with theta also could serve as the argument. Yeah, so this is kind of confusing to think about. You know, there's only one plane of complex numbers, and so you would think that, well, so angles couldn't go past 360 because it's like you're going into a separate plane, but you have to think about it from just a pure mathematical standpoint, that if you wanted to locate a point in the complex plane, you could use this formula, and you could technically use an angle that's coterminal with the main angle between 0 and 360. The math is still going to work. It makes it kind of confusing because it's like when you go past 360, are you changing planes? No, because that's just the way the trig functions are defined. That's the way angles are defined. It's all about, you have to think about it from the perspective of this complex plane of numbers doesn't know anything about a coordinate system. So if you wanted to specify two parameters to locate a point in the plane, you could plug in an angle that's like greater than 360 but coterminal with the main angle, the angle between 0 and 360, and the numbers are going to come out the same. The coordinates are going to come out the same, that's the whole idea. So yeah, but like generally we're going to think about angles between 0 and 2 pi and 0 and 360, but you could still locate points in the complex plane with angles greater than 360 or negative angles, etc. Okay, so how can we have this? Here's a complex number in polar form, or trigonometric form. They call that trigonometric or polar form, and we want to write it in rectangular form. How can we do this? Well, okay, it's in polar form, so we know R and we know theta. Okay, so all we need, we're trying to write it in this form, x plus y I. Well, we know x is r cosine theta. Y is r sine theta. Easy, just plug r and theta in here. And that's what they do, and they get that it's 1 minus I root 3. And it's important to note that that these two represent the exact same number. 1 minus I root 3 and this 2 times cosine 300 plus I sine 300 represent the exact same number. It's important to realize that. Like, those two are equal. You can set those equal. Okay. Converting between rectangular and trigonometric form, so going the other way, yeah, this is going to be simple. You're just going to, if you've got x plus yi, then we know that, so r is going to be the square root of x squared plus y squared, and then, so you can get r, and then tangent theta is y over x, so, but you're going to know what the quadrant is because you have x and y. So you can just use tangent to get the reference angle. I guess it'd be easier to just get the reference angle. It'll give you, this will give you a positive or negative angle, but you know that it's going to be the absolute value of that's going to be the reference angle. And since you know the quadrant, you can just get the actual angle. So, okay, like here, write this in trigonometric form. So you've got, let's see, that x squared minus root 3 squared is 3 plus 1. So r is equal to 2. Okay, now we've got tangent. Well, we know that we're in, let's see, this would be quadrant 2. We're in quadrant 2, so we've got tangent theta is, let's see, 1 over minus root 3. So we've got the 30, 60, 90 triangle, but they want us to do this in radians. But, okay. So 1 root 3, 2. Tangent of 30 is opposite over adjacent. So it's going to be minus, what's going to come out of this is minus 30 degrees, but like 30 degrees is the reference angle. We're in quadrant 2, so what's that? 180 minus 30, 150 degrees is theta. r is equal to 2, theta is equal to 150 degrees. But we want to put that in radians, so what's that going to be? 150 5 pi over 6. So r is equal to 2, theta is equal to 5 pi over 6, and you just put it into that form. It's r times the cis theta, cosine theta plus I sine theta. Just plug in 5 pi over 6. So that's what they do. 2 times cosine 5 pi over 6 plus I sine 5 pi over 6, or 2 cis 5 pi over 6, just like that. Okay. What about minus 3i? Well, okay, we know that's going to be, that's not in a quadrant, that's a quadrantal angle. They want to use degree measure. That is, theta is equal to 270, and r is equal to 3. R is always positive. R is equal to 3. So we've got 3 cosine 270 plus I sine 270, or 3 cis 270. Again, that's rectangular form, and then we put it into polar form. Okay, now converting between trigonometric and rectangular forms using calculator approximations. So yeah, all they're doing here is that we're not going to have special angles like cosine 125. That's not a special angle. You put it in the decimal form, right? So here's they went from polar to rectangular, but there's the components are in decimal form. Okay. Now, last thing we want to talk about in this section is, so it says an application of complex numbers to fractals. And so yeah, at the image at the opening of the chapter, the opening image talked about fractals. So at its basic level, a fractal is a unique, enchanting geometric figure with an endless self-similarity property. A fractal image repeats itself infinitely with ever-increasing dimensions. If we look at smaller and smaller portions, we will continue to see the whole is much like looking into two parallel mirrors that are facing each other. Yeah, it's like when you go to the carnival and the fun house, it's like those mirrors that are infinitely, it's like your image is infinitely repeating. It's kind of like what a fractal is. You can zoom in forever, it seems. And the pattern is like repeats. Okay, so what does this have to do with complex numbers? All right, deciding whether a complex number is in the Julia set. The fractal called the Julia set is shown in figure 11. Okay, there's the Julia set. To determine whether a complex number z is equal to a plus bi is in this Julia set, perform the following sequence of calculations. So you take the complex number, you do z squared minus 1. Like we know how to square a complex number, right? They're saying you do a plus bi squared minus 1. Then you do you write that down. Then you do another calculation. You say z squared minus 1 squared minus 1. You write that down. Then you do this and you write that down. And you keep going. There's a pattern here that you keep like squaring. They squared this and then subtracted 1 at the back end. Then they squared all of this and subtracted 1 at the back end. That's the third term. You see, you start with z squared minus 1. Then the second term you square this and subtract 1 at the back end. Then the third term is you square all of this and subtract 1 at the back end. So you just keep doing that. All right. Now, if the absolute values of any of the resulting complex numbers exceed 2, so the modulus, you're always going to have every number that exists as a complex number, but like even this is a complex number, right? The modulus in this case would be 4. It's because that's the only component. But maybe you end up with a non-real complex number, but you can still find the modulus. Okay, now, if the absolute values of any of the resulting complex numbers exceed 2, then the complex number z is not in the Julia set. Okay, yeah, so they're talking about the modulus here. You're going to end up with a complex number every time. Even if it's just like a pure real number, it's still a complex number. Or you might have something like this. You can have each of these is going to be its own complex number. And remember, the modulus is, they call it the absolute value because it's always positive, because it's that r is equal to x squared plus y squared. This is always positive. But like if you have just a real number, like if you just had 4 plus 0i, the modulus is 4, or the absolute value, same thing. if it was 4 minus 3i, the modulus would be, so 16 plus 9 is 25. The principal root of 25 is 5. The modulus would be 5. So it's saying you calculate the modulus for each of the complex numbers here, and if any of those values exceed 2, then the complex number is not in the Julia set. Otherwise, it is. And then what they're saying is, if it is, then you go ahead and plot that point in the complex plane. If it's not, then you don't plot it. And what results is, if you do that, these are the ones that you're gonna end up plotting, and you're gonna get this shaded area here, which I'm assuming ends up being a fractal. So okay, the next thing they do is they determine if these two numbers are in the Julia set. We're not going to do that, but I'm not sure what the point of this is. What I mean by that is, you could do this. What does this have to do with complex numbers? We could do this with any. We could have done this with any XY plane. With any, I could have made a plot between price and cost, an XY plot, and I could have seen if certain values are in the Julia set. Well, I don't understand what this has to do with complex. Why is this so specially related to complex numbers? Okay, so let's see. They just calculate if these two numbers are in the Julia set or not. Okay, well, let's come back to the image at the start of the chapter. So, all right, it said high-resolution computer graphics and complex numbers make it possible to produce the endless self-similarity property of a fractal image. So I guess it must be that with your ability to you can represent points in a plane with complex numbers, but like if it's just an XY coordinate system, then there's no like relation between X and Y at all. There's no, the idea of multiplying X and Y doesn't mean anything. But I guess with complex numbers, the fact that you can multiply them and there is like more of a meaning to it, I guess it must allow you to give you more versatility with working with like things in a plane, planar images, etc., planar graphics. So yeah, interesting.